When you ask a large language model to write code without global architectural context, the result is a fragmented script that fails to compile. The solution is to establish master system instructions before inputting a single prompt. This global configuration dictates exactly how the AI interacts with your codebase. The first step is defining a strict developer profile. By explicitly telling the LLM that you build production apps with React, TypeScript, and Shopify Liquid, you eliminate assumptions and force the output to match your specific tech stack. Next, you must enforce rigid communication rules. You instruct the AI to explain what a block of code does before showing it, forcing the model to validate its own logic prior to generating syntax. We must also define custom operational keywords. A command like audit triggers a comprehensive review of functionality and accessibility, while trace commands the model to follow parameters through an entire call chain. These instructions force the model to evaluate the broader project structure before it attempts to generate any logic. This diagram maps the master node, establishing global operational constraints. The first constraint is type safety. We mandate the use of strict TypeScript interfaces for all parameters, explicitly forbidding the use of loose any types. The instructions also enforce UI standards. Every generated component must default to mobile-first styling and include complete area accessibility attributes. For asynchronous operations, we inject parameter flow tracking rules. The LLM is required to wrap all async calls in a try-catch block and provide specific console log outputs for error handling. External integrations require global API rules. We instruct the model to always route browser-based API requests through a specified CORS proxy, and to immediately write standard fallback procedures if that proxy fails. Establishing these technical boundaries means generated components arrive with pre-validated prop types and standardized error boundaries already in place. This tree represents a multi-file application architecture, UI, state, function, and API layers. In deployment, these inevitably fail due to state mismatches. The most dangerous are silent failures. A function halts execution, but the console registers 0 errors to point you toward the issue. Pasting the broken file into an LLM and simply saying, "This doesn't work," fails, because the model lacks the cross-file context to see where the execution stopped. To find silent failures, we use the data flow trace protocol. This is a structured prompt forcing the AI to analyze the complete lifecycle of a parameter. The trace begins by command the LLM to locate exactly where the parameter is captured. Next, the prompt forces the AI to track how that parameter is passed down through props. Finally, we instruct the LLM to insert console log statements at every single junction along that route to verify the flow path. Forcing the AI to map the exact route of a variable exposes the precise point of failure, bypassing the limits of single-file syntax checking. The next major architectural hurdle involves TypeScript function signature mismatches. When a function's parameter definition is updated in one file, its external call sites across the rest of the application remain outdated, breaking the build. We use a specific prompt instruction to align the parameter order. We explicitly command the AI to apply optional default values, using the question mark syntax, to prevent breaking existing calls.
This visualization demonstrates forcing the LLM to update all dependent call sites simultaneously across the entire project. This multi-file update guarantees expected data structures align perfectly, preventing cascading type errors across the component tree. Treating function signatures as strict cross-file contracts ensures the AI maintains type safety across the application. External integration failures require an entirely different set of diagnostic protocols. An established API connection will eventually return a 429 rate limit error, halting the core functionality. To diagnose this, we use a prompt to isolate CORS proxy failures from standard network timeouts. First, verify the endpoint URL formats, check the authentication headers, and confirm valid access tokens. If the primary CORS proxy goes down, the protocol commands the AI to automatically write alternative fetching mechanisms to restore the connection. Finally, we prompt the LLM to define strict TypeScript interfaces for the incoming JSON response. This ensures the data is parsed correctly, preventing undefined mapping errors when an array is empty. Utilizing structural prompt constraints turns opaque external API responses into auditable, repairable data pipelines. This sequence illustrates the culmination of the framework, deploying complete, domain-specific micro-applications using a single, massive prompt. A successful one-prompt app requires a heavily constrained template. Standard LLM code generation fails because it relies on assumptions. Templates leave zero room for interpretation. The first component of the template explicitly defines the platform architecture, such as demanding a Vite, React, and TypeScript stack. The second component is a precise, itemized list of required UI and UX features, dictating exactly what dropdowns, inputs, and generation buttons must be present. The third component injects deep domain context. We feed the model the specific brand voice, target audience, and required industry certifications, such as GOTS certified organic cotton. The fourth component outlines targeted third-party API integration instructions, defining how the app should interact with external AI or storefront endpoints to format its outputs. These dense prompt constraints interact securely with the global system instructions established earlier, ensuring the code output adheres to your strict personal coding standards. Strictly defined templates dramatically reduce output variance, consistently yielding reliable scaffolding that flawlessly matches the architectural requirements of the project. This diagram shows the collection showcase generator, a practical application of this prompt taxonomy mapping directly to a structured UI. The prompt specifies a direct connection to the Shopify admin API, commanding the app to fetch existing store collections securely through a proxy. Because we injected the brand's domain context, the prompt dictates the automatic generation of SEO-optimized descriptions and meta tags specifically tailored to those incoming collections. The template explicitly ensures the LLM builds the necessary React state management, allowing users to toggle through those collections using native drop-down selectors. This still shows the final output, a fully deployable React application that integrates third-party APIs right out of the box. When system directives, cross-file debugging strategies, and strict templates combine, the AI functions as a predictable architectural component of the development workflow.